To ensure that we select the appropriate pump for our system, there are a number of considerations that we need to make. First, I want to draw your attention to this figure that's been inserted here, where there are several lines shown here, and we'll describe each one in turn. But first I want to point your attention to the solid black line that's curving downward. That is the pump performance curve. And the solid gray line that curves upward, that is the system curve. In order to select the correct pump, we want to see where the operation point of the pump is, and it's going to be where the pump performance curve intersects with the system curve. From there, we can start reading off some of the performance values of the pump to see if whether or not they're good enough for our system. So in the first case, efficiency. We want to know that we are operating at or near the best efficiency point of that pump. So if we go from our operating point and draw a line upwards and over to read off the efficiency, we can see that our operating point is pretty darn close to, essentially at, the best efficiency point of the pump performance curve, which is drawn by that orange dotted line. The ideal situation would be at it, but we don't always get there. So we just want to be near it. That's the ideal, just being close to it. But when we talk about efficiency, you may think, well, what are we talking about in terms of efficiency? Well, for pumps, if we put a gauge on the downstream side of our pump, we could measure discharge and head coming out, right? And if we use this formula here, we can calculate what is known as the water horsepower. In other words, the amount of power that is observed in the discharge and the amount of pressure head that's coming out of our pump. In order to generate that water horsepower, there was a certain amount of power that was applied to the shaft of the pump, which then loses a bit of the energy as it applies to the water. The amount of power that is applied to the shaft of the pump is known as the brake horsepower. And this, you can see the only difference between these two equations is now we're accounting for the efficiency of the pump. We can read that off this chart by, again, drawing a line up from the operation point to where it intersects with the brake horsepower line, and then drawing a line over to the left horizontally to read off the brake horsepower value. Or we could just simply use this equation to calculate it, because that's what they did to create this chart. Taking one step back, we could calculate the total horsepower, which in this case accounts for the efficiency of the motor. In other words, there's a certain amount of electricity that comes out of the wall and gets inserted into the motor, and then the motor converts the electrical power from the wall into mechanical power applied to the shaft of the pump. So the only difference between that equation and all the previous one is, as you can see, the efficiency of the motor term. And this is helpful for us because we want to know how much power is required to operate a pump. For every 1 horsepower, we have 0.746 kilowatts. And for those of you who pay power bills, know that our energy is billed to us in kilowatt hours. So this will give us a tool for determining what is the cost of operating our pumps. By the way, if you wanted to use these formulas for water horsepower, brake horsepower, and total horsepower in English units, meaning we insert gallons per minute, you just swipe out the 550 and insert 3960 into those equations. The third consideration we want to make is something that's called the net positive suction head. Net positive suction head is a pressure head that needs to be maintained in order to avoid cavitation inside the pump. Cavitation is a process where gas is extracted from the fluid, either because the swishing of the blades of the impeller or because of the temperature of the water or what have you. But gas bubbles will, instead of dissolve, be extracted from the fluid and begin to form on the impeller blades. And as the impeller blades continue to operate, they will smash these little gas bubbles to the point where the gas bubbles will explode on the blade and pit the blade. So we don't want cavitation to happen because it shortens the life of our pumps. It is also a noisy process. It is also very dangerous or damaging to the equipment that is anchoring the pump in place and trying to keep it from, vibrating itself out. So we want to avoid cavitation at all costs. Every pump has a required amount of net positive suction head that is a function of the impeller diameter, the volute, the rotational speed of the pump, and so on and so forth. So when the manufacturer designs the pump, they run a test and create this last curve that you see on the bottom of this chart that's curving upward to plot this curve. They say, well, at increasing flow rates Q, the net positive suction head that's required to safely operate this pump also must increase. Which makes sense, like if you're in a tub, the faster you swipe your hand through the water, the more bubbles you'll generate, I presume, right? Slower you go, you may not generate any bubbles. And that we can read by just drawing a line straight down from the operation point to the net positive suction head required line and then over to the amount of head that's needed. There's also, in our system, a net positive suction head available. This we calculate from our system characteristics, meaning we calculate it using the length of the pipe that led from the storage to the pump, its diameter of that pipe, the friction coefficients or the roughness of the pipe. We also take into consideration the elevation of the reservoir and the elevation of the pump. We want to know how much static head is already resting on top of the pump. Net positive suction head available is also a function of atmospheric pressure. The atmosphere does help keep gases dissolved in liquids, so we like that. And then, as I mentioned earlier briefly, there is this net positive suction head available as a function of the temperature of the water, so what we call vapor pressure in the water. So as the temperature increases, it is less likely that gases will remain dissolved, and so you might see more gas generation, and therefore you need more net positive suction head available if you're going to be net positive suction head if you're going to be pumping hotter liquids. Likewise, if you have a lot of organic content that you're pumping and it's a wastewater treatment plant of some sort, organic content attracts microbes. Microbes consume the organic content, and microbes can produce gases as they consume the organic content, and that generates bubbles all by itself. In theory, one could say, hey, we just want the net positive suction head available to be slightly bigger than the net positive suction head required, but in practice, we usually say for water applications that the net positive suction head should be greater than the net positive suction head available should be greater than the net positive suction head required plus about 5 feet for typical water applications. Because of the whole organic content problem we just discussed, for wastewater applications you probably want an additional 7 feet of net positive or above the net positive suction head required. So these are some of the considerations in the simplified format that we make in order to decide if a pump is sufficient for our system.